VC Calc students, this is going to be your day 43 notes. Today we're going to look at some more properties of integrals. And to get started, we're going to evaluate this definite integral, and we're going to do it in a little bit of a different way. We're going to be able to do this without even using math number 9. I'm going to show you how you can do this in y equals. If you graph the function x squared, how there's a function in the calculate menu that will allow us to calculate the area under the curve. And it's actually pretty cool. I think you'll like it. But just to kind of connect back to day 42, we can write this as what's called a Riemann sum. And this will come up in some of the homework questions, as well as recognizing this not only in its current form, which is using that really nice Leibniz notation with our integral symbol, but as a Riemann sum, it would be the limit as the norm of the partition P goes to 0, right? Like that's the largest partition as that goes to 0, all the others do. From k equals 1 to n. In this case, what we're looking at is we're looking at the heights on the function x squared. So we'll see that denoted as c sub k squared times the dx, which dx are going to be the widths. So that's going to be delta x sub k. So this is a really generalized way of writing this integral for the area under the curve of x squared in general. But just connecting that, this is what it looks like as a Riemann sum to here's what it looks like in our kind of nice cleaned up notation. This will be a connection that you have to make on the homework. But let's kind of take a look at what it looks like on the graphing calculator. So on your calculator, you're going to go to y1. You're going to just type in x squared. So that's pretty easy for us to do. Go to y equals. We'll type in x squared. And then once you have in y1 x squared, if you hit zoom 6 just to make sure we graph it, and there's our good old function y equals x squared. If I want to find the area under the curve from -2 to 5, just to kind of make this a little bit easier, you'll see that at x equals 5, we don't have the y value yet because we know the y value is 25. So maybe I'll make my y max 30 just so we can see how far out this area is going to go. So once you have your window set there, we're going to go to second trace, which is that calculate menu. And we're going to calculate, you'll see in a second, option number 7. So what is option number 7? You probably haven't used it too much before. Second trace, option number 7 is the area, the integral of f of x dx. So here we go. What is the lower limit? Well, the lower limit is -2. Hit enter. What is the upper limit? Hit 5. Enter. And it's so cool because it shades that area for you. So I think that's pretty neat. So graphically, what we're seeing is from -2 to 5. Here's -2, here's 5. It shaded all that really nice area in for us, which is pretty cool. Oh, and by the way, the area under the curve is, according to the calculator, 44.3 repeating. Okay, so we could just as easily have used math 9 for this to calculate the value of this finite integral, but just a different perspective. If you're looking at things graphically, considering the area underneath that curve, this is a really nice visual to show what we're actually calculating in this case. Okay, we've already talked about from day 42 that in some cases, if the heights of the function are negative, that we may in the end wind up getting some negative valued areas in terms of the accumulated area altogether for our function. However, one thing to consider here is if I want to find out what the area is equal to, what I mean by area in this instance is what is the total area? And total area is different than accumulated area. So we know that the area, according to this nice little graph here, we know the area from A to C. And by the way, the reason why it goes from A to C and not from A to B is usually the endpoints of the definite integral are from A to B. We know that the area from A to C is positive, so I can take the integral from A to C of this function f of x dx. And then because we know that from C to D the area turns negative at this point, if I want total area, we're going to negate the integral from C to D of f of x dx. Okay, and that will now return a positive amount to give us the total area. In other words, if I wanted to paint this image right here, how many, square units of paint would I need? Well, we need to turn that to positive then. Then because the green section's nice and positive, leave it as plus from d to e, the integral of f of x dx. And because that last region goes negative, we're going to subtract from e to b the area there for f of x. So this is definitely one way to write the total area underneath the curve for this expression, including those negative heights along the way. Now, it's good to know what this format looks like, because I feel like this will be a typical way that we can calculate some areas, or if it's easy enough for us to represent it in this format, you could say that the total area is the entire interval from a to b of the absolute value of f of x. Because that would do the same thing, that if I took the absolute value of f of x, it's going to turn all these negative areas, it's going to flip them up and make them into positive areas. So this would be another way for us to evaluate the total area under the curve. Now, if we're doing this by hand and we don't have a calculator, I think we're going to find that taking the integral of an absolute value is going to be challenging for us. So we might then, in this case, break it up into these little intervals along the way and just choose the appropriate positive negative cases. So just keep in mind that the difference between this and then the accumulated area would just be the straight up integral from a to b of f of x dx. Okay, and in the end, it might come out positive, it might come out negative. You know, based on this, it kind of looks like it's more positive than it is negative in the end anyway. So it might wind up being a positive, but it's not the total area. It's just what the accumulation of areas would equal as I go from a to b. So just the difference between those two, it's important to take note of. On to the next page. On the next page, we have at the top that definition of the definite integral again, according to what we did just on the front there. It's the limit as the norm of the partition goes to 0 for the sum from I equals 1 to n of, in this case, these are the heights of the function times the widths. That is equal to the definite integral from a to b of f of x dx. So to practice on the graphing calculator with these, what I'll tell you is let's just do math 9. We saw how we can use the feature of finding the area for second calc number 7 earlier. But for something like tan x, if I want to think about just graphically quick what this looks like from 0 to 1, we know the tangent function crosses through the origin, and then it's going to go up like this until it reaches its asymptote at pi over 2. But the area under the curve from 0 to 1 is this positive valued area region to start. So to determine that from the calculator, we're going to very quickly, on the calculator, do math 9 from 0 to 1 of tan x dx. Just make sure that when you're doing this that you are in radian mode. Okay, you're going to get a different result than you might desire if you're in degree mode. And we can see that that's in 0.616. Okay, so the area under the tangent curve from 0 to 1 is approximately 0.616. And I think at this point, you can try these two and just make sure that you're getting the same answers from Math 9 and confirming that you're all set to use that feature. This I'm just going to tell you is 1.718, and we know what e to the x looks like, right? So e to the x is this function here from 0 to 1. We're looking at this area right there. And then from -1 to 0, similarly, type that into Math 9. You get 0.632. Still a positive valued function on the interval from -1 to 0. Just a smaller area on this side of the x-axis. Okay. So if you want to confirm those two by using Math 9, go for it. Those are what the answers that you should get to each of those, which brings us to properties of integrals. Now, these properties of integrals are very similar to what we've seen with properties of derivatives. So if you think back to derivatives, the derivative of a sum is equal to the sum of the derivatives. That's true. The derivative of f of x plus g of x is equal to f prime of x plus g prime of x. Well, that's also true about integrals. If you have the integral from a to b of f of x plus g of x, that would equal the integral from a to b of f of x plus the integral from a to b for the function g of x dx. And here are just some other quick integral properties. If you have an integral from a to c that you want to break up into two different pieces from a to b and then b to c, we'll see why we're going to do that actually in just a minute. This would hold true, that we can find the area from A to B, from B to C, and add them up. That gives us everything from A to C. All right, well, this should make sense. The area from A to A is 0. Okay. No area under the curve if we're looking at the area from A to A. If you're multiplying your function by a scalar, k, you can kind of bring that scalar out front. You can find the area from A to B for your function, f of x dx, and then multiply that end area by k. And finally, for the last case here, if you reverse the bounds, and this will be something that happens here and there, that instead of going from A to B, if you reverse it and go from B to A, it winds up equaling the negated value of the integral from A to B for f of x dx. So why does that happen? Well, it happens because if you think about what delta x is over here, delta x would equal the difference in b minus a over n. Right? You would take the difference in those bounds and divide by the number of subintervals, which in general is n. Whereas over here, delta x is a minus b over n. So to get those to match, if you negate the delta x, that's going to give you b minus a over n. So therefore, negating delta x is why we can think of this as being the negated integral to match this integral over here from a to b. Okay, so just in the end, we have to know that if the bounds are reversed, but it's the same function, we're going to get the negated area. It's kind of like working backwards from one endpoint to the other. And when you do that, it's kind of thinking of it as like a negative accumulation of area. Okay, so if we look at these two examples here, the integral from 0 to pi for sine x dx, I feel like we did this in the lesson yesterday, but if we didn't, if I'm not remembering that correctly, let's see what Math 9 tells us here. So the integral from 0 to pi of sine x dx is going to wind up equaling 2, interestingly enough. Okay, so we get that this is equal to 2. And without doing anything else, I know that if I reverse the bounds, that this is going to equal the negated form of this area right here. So you can use the property of integrals to say, oh, this is the same thing as negative 0 to pi for sine x dx. And the reason why we might have to know that property is if we don't know exactly what our function is. So if I just said from 0 to pi, f of x dx has an area of 2, we would have to know from pi to 0 that it's the negated value there, which in this case is just going to be negative 2. Okay. So using that last and final property there, that should be pretty easy for us to evaluate. All right, moving on to something that we saw as far as the integral existence theorem. This was in your notes from day 42. If f is a continuous function on the interval from a to b, then the area under the curve from a to b of f of x dx is equal to, and again, this is our notation for the limit as the norm of the partition goes to 0 for the sum of the heights times the widths in this case. We know that it exists and is the same number for any choice of the number c sub k. Okay, so this is our very generalized form of generalizing the area under a curve, our definition of an definite integral here. So what about if it's a discontinuous function? You can see that discontinuous function that I've drawn below, and you might then start to see some of the shadings that I have here. Something that I'm going to put on my x-axis is just labeling some of these. So just for fun, I called this 2, I called this n.4, I called this n.5. So even though the integral existence theorem only states that this is true for continuous functions, if we have a discontinuous function, we can use our property of integrals to say, you know what, I can find the area under this curve from 0 to 2. I can find the area under this curve from 2 to 4 and then break it up into the last section, find the area of the curve under 4 to 5. That will give me the total area under this discontinuous function from 0 to 5. So you're just going to break it up into pieces, just like one of our properties suggests, right? So that was the property I was alluding to in number 2 right here, that the interval from a to c, this is really going to help us out if we have a discontinuous function. It's the same as the integral from a to b plus the integral from b to c. So we're going to have to separate this and split it up in the event we have a discontinuous function, and that's going to look like this then. So the total area under the curve from 0 to 5 would be the area from 0 to 2, plus the area from 2 to 4, plus the area from 4 to 5. And then we'll put that idea into practice in our next example right below this. So if you take a look at example 2, we're going to put this idea into practice. Okay, so this might be a function that you're somewhat familiar with, the absolute value of x over x. If I want the area under that curve from -2 to 4, we have an issue at a certain point of discontinuity, and that point of discontinuity occurs when x equals 0. So if I think about what the graph of this looks like, we know that when x is a negative value, that the output here is going to be -1, right? Absolute value makes it a positive quantity, but we still have that negative quantity in the denominator. So to the left, from -2 until I get to that point of discontinuity at 0, the output there is -1. So you're going to get a graph that looks something like this. And then when you get to x equals 0, on the positive side here, anything you plug in for x would return a +1. So the graph looks something like this. And we're looking at that until x equals 4. So the area that I'm trying to determine here is the area from -2 to 0 plus the area from 0 to 4. So in order to evaluate this integral, we're just going to go ahead and separate this into those two pieces. So this would be equal to the area under the curve from -2 to 0 of the absolute value of x over x dx plus the area from 0 to 4 of absolute value of x dx. And the nice thing is that because I've drawn this picture, I know what those two things equal. Because these are these nice constant functions to the left and right of 0. I know that the area from -2 to 0 is going to wind up being, this is a 2x1 rectangle right here. Now, because it's below, it depends how I'm asking this question, right? Am I looking for accumulated area or total area? Well, we'll kind of answer both. If we do accumulated area, that's -2 plus, this is a rectangle that's a length of 4 and a width of 1. So this is going to be -2 plus 4. So the accumulated area in total from -2 to 4 is +2. But meanwhile, the total area, you would have to negate this function, right? Because it has a negative area. So we would say that it's +2 plus 4 for a total area of 6. So we just want to make sure that if we're answering a question that involves positive and negative areas, we want to make sure we're looking for either accumulated area or, in the end, the total area, which would involve us potentially negating some sections that have negative areas. Okay. So if we're good with that one, breaking up a discontinuous function, what about the next example? In the next example, it says, is the integral from 0 to 5 of f of x dx positive or negative? Which one is it? Well, I think you could probably tell pretty quickly that here's my positive area right here, and then here, and I'm just making a guess at it, here's my negative area. It looks like we have a lot more negative area than we do positive area. So I would venture a guess, even though we don't know the exact function here, that altogether, the integral from 0 to 5 would be a negative area. So then write an expression for the total area. I would hit pause real quick, just make sure you're pretty good at doing this at this point, because we talked about this earlier in the lesson, but I'm going to write my answer right now. It would be the area from 0 to 2, that's all fine, right? If we break this up into two different integrals of f of x dx. And then we're going to subtract that negative area from 2 to 5 to turn it into positive area of f of x dx. So we can do that, or maybe the quicker and easier fix is by saying take the area from 0 to 5 of the absolute value of f of x dx, because that's going to automatically turn all these negative y values to positive y values and kind of flip that negative area above the x-axis. So we could fix it pretty easily that way too. If you look at this really shaky, wobbly looking graph of y equals f of x, what I want you to do is see if you can try these on your own. And they go so fast. So you should be able to do this pretty quickly, but find the area from 0 to 3, find the area from 3 to 7. And remember that we're looking at, for now, accumulated areas. So if we're above the x-axis, these are positive areas. If we're below the x-axis, we want to make sure we're considering those as negative areas. You should be able to fill these in pretty quickly. We'll go over them next time we're together in class. Make sure you understand the difference between parts E and F specifically. The absolute value location will make a difference. So take a look at those. What we're going to kind of wrap things up with today is looking at what is known as a Riemann sum in disguise. And we should know how to do Riemann sum in disguise based on the fact that we know how to do, this is really a derivative in disguise, isn't it? We've done this somewhat recently. What derivative is this in disguise? Well, according to the limit definition of derivative, the limit as h goes to 0 of x plus h cubed minus x cubed over h is the derivative of the function y equals x cubed. So without actually expanding this out and doing the limit definition here, I know that the answer to this is the derivative of x cubed, which is 3x squared. It may not be as simple when we do backwards Riemann sums, but when you have this limit as n goes to infinity of this expression, what we're going to start doing is we're going to start to try to break this expression up into heights of a function times the width of the function. So we want to break this up into our areas, because then if we take the limit as n goes to infinity of this sum, that's the definition of the definite integral. So we're going to eventually be able to take this Riemann sum and convert it into what we know according to the definition of a definite integral. So here's what we're going to do first. I'm going to break this denominator apart into the cube root of n times the cube root of n cubed. And you're going to see why we're going to do that in a sec, but let's rewrite this as the limit as n goes to infinity of cube root 1 plus cube root 2 plus dot 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 cube root n all over cube root n times over here. I'm going to separate this cube root of n cubed, because what is the cube root of n cubed? Isn't that just n? So since it's in the denominator, I'm going to multiply this whole thing by 1 over n. And to go one step further with this, I'm going to write this as the limit as n goes to infinity of, you can actually start taking these and dividing them by the cube root of n and writing it as the expression cube root of 1 over n plus cube root of 2 over n plus dot dot dot. At the end, you're going to get the cube root of n over n times 1 over n. And what we have on the inside here is we have a series, don't we? Right? We have the sum of all of these terms, where the denominator is always n, and it's the cube root of, well, it's 1 and then 2 and then all the way to n. So these are just kind of going up by 1 each time. So what we can do is we can write this as a summation. So we're going to actually bring all this in to a summation of the limit as n goes to infinity of, it's the sum from, I'm going to use the variable k, so from k equals 1 until I get to the last term where the numerator is n, of the cube root of k over n times 1 over n. Now, take a second to really make sure that this makes sense to you, that if I were to evaluate this sum right here, I would plug in 1 for k, and then 2 for k, and then 3 for k, and I would get these terms in this series right here. And then the last term I would get was by plugging in n for the value of k up there. Still times that 1 over n. And what this is turning into is that this is turning into the definition of a definite integral, where these are going to be the heights of the function, and 1 over n is going to be representative of the width of all of our rectangles. So which function are we integrating? And it's a pretty easy choice once I think about if I'm looking at these as my heights, the cube root of something is a height. Why don't we say that we're integrating the cube root of x? Okay, so here's what we're going to do. We're going to let x equal the quantity under the radical, k over n. And therefore, the function that we're integrating, f of x, is therefore the cube root of x. Right? If we let this equal x, the function in question that we're finding the integral of is cube root of x. But what we don't know is we don't know the bounds yet. So we know we're taking the definite integral of the cube root of x dx over some bounds right here. So how do we find the bounds? Well, what we're going to start by doing is when I talk about the lower bounds, the smallest value that we can plug into this summation is when k equals 1. So the lower bound occurs when k equals 1. So what that means is if k equals 1, then x would equal 1 over n. Remember, we're taking the limit as n goes to infinity. So what is the limit as n goes to infinity of 1 over n? Well, that's pretty easy. That's just 0. So that gives me that the lower bound of this definite integral is 0. And similarly, the upper limit, I'm running out of space here, but the upper limit is when k would equal the upper limit of my summation, which is n. So if the upper limit occurs when k equals n, then x would equal n over n, if x equals k over n. So then here, the limit as n goes to infinity of n over n, well, that's just 1, because n over n is 1. That becomes the upper bound of my definite integral. And now that I have the function and the bounds established, this initial problem right here was our Riemann sum in disguise. We can, in the end, write that as the definite integral of the cube root of x from 0 to 1. And now we can just math 9 this. So if we math 9 from 0 to 1, the finite integral of the cube root of x, oops, not square root. Let's try that again. So we'll do math 4, cube root of x dx. We're going to get final answer of, think about, it turns out to be 0.75. And we'll eventually have other techniques to evaluate this without the calculator, but we'll have 0.75 as the answer here. Okay, so this can be a tough process. And I realized that, we did a lot of work to break this down to eventually be able to write it in that form for our definition of a definite integral using that Riemann sum look. But we'll do another practice question tomorrow in class. This last one, it says to try it, but I'll leave that up to you. If you want to see if you can give it a shot and see if you can use the technique and the strategies that we used over here, it's definitely a very similar question, right? I'll give you even a little bit of a hint. You're going to break up n to the 4th into n cubed times n in the denominator. And then you can start kind of breaking this apart and eventually determining a function to represent all the sum of the heights times the width, okay? So if you're unsure about where to go from there, don't worry about it. We'll do that next time in class and get some more practice with that concept. Otherwise, that's it for day 43. If you have any other questions, let me know next time I see you in class. Have a